want you to explain why you saw what you saw. Nope, not that. It's this one. This will really scare me. Kill these guys. Oh, hang on. I gotta do one other thing. Sorry about that, folks. I gotta check the sound level. Because I muted it, I think. Yes, okay. That will work. All right, here we go, ladies and gentlemen. Explain to me what you see.
Hey, carbonated beverage. Tell me when you're ready.
We're ready.
A cola carbonated beverage here at 2.5 atmospheres, somewhere deep below the sea. This you should never try at home. Shaking up your Coke, because you know what's bound to happen when you take your Coke and you open it up and it sprays all over the room. Didn't happen.
Pressure.
I said don't say anything out loud. Oh, that just cost you 1 million points. Mental note. Because you gave away half the answer right there with one single word. He now has to explain it in detail.
Yeah.
So the answer is?
Pressure?
Pressure.
There's higher pressure because they're at 2 atmosphere.
Yeah.
So, something.
Something, something.
Let's go to D.
Who wants to help him out? Dave?
Well, at 2.5 atmospheres, the partial pressure of carbon dioxide in the atmosphere surrounding the Coke can would be 0.010, because it's 0.004 at 1 atmosphere, sometimes 2.5, and
Yeah.
that must be greater than the partial pressure of CO2 inside the Coke can as pressurized at the Coca-Cola bottling factory.
So why does anything go anywhere? What am I trying to make you guys always realize?
Differences in partial pressure.
Right, pressures, okay? Now, just out of curiosity, now we'll do this. Anybody recognize who that was? See, that's a sorry state of existence. You gotta work on that.
Happened. Look at that. That's
Now, listen to his explanation. This is really sorry. This is Chris Hadfield, a cosmonaut, who actually got permission from David Bowie to sing Major Tom. He actually composed it while he was in the space station. Yes, which is really kind of cool. You can actually watch a YouTube video of it. He's a phenomenal researcher and scientist, but he should feel really, 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 really embarrassed with what he's about to say.
physics in motion right there. Archimedes' principle or Boyle's law or something like that.
Ohm's law, Pythagoras.
Ah, a nice little fizz.
P
All right.
squared plus B squared
There we
equals
go.
flat code.
One of the advantages of living under the ocean. Thank you.
Totally fucked that up. Yeah, which gas law is that, by the way? That's Henry's, right? Just looking at it in reverse. So you get really, really bored, look up Chris Hadfield singing Major Tom on the space station. He actually was a member of a rock band. The guy is disgustingly talented. All right, let's get on to the real world here and look at what some of you are recognizing as, oh my God, this thing's really scary. All right, don't let it be scary. Break it down into pieces. You need to know everything that's on here, as I warned you guys before. So approach it in segments. First learn the gas values in the atmosphere, then go down and learn the gas values in the lungs, and then go clockwise around this whole little system. Learn what it is in the arterioles, then memorize what it is in the tissues, then memorize what it is in the lungs, and then most importantly, make sure you understand why gases will go where they're going with this. What is the ultimate source of O2? Where does your O2 come from? That's in your body. Where did it come from? Well, in a sense, true, right? Whether it's zooplankton or phytoplankton or plants, but really the air, right? And what's your ultimate source for CO2? Where did the CO2 come from that you exhale? Oh, that's scary. What organelle generates CO2 in your cells? First group, we got to get you guys to. You got to give everybody else a chance. Shut up! Right? You all should be saying mitochondria, right? Right? Yeah? Oh my God, you guys are giving me a heart attack over here. All right, let's move on. A little bit of review. Right? Blood cells. I know they have hemoglobin. It has 4 protein globulins, 2 alphas and 2 betas if I'm an adult. If I'm a child or a newborn, I should say, I can have maybe 2 alphas, 2 gammas. In the middle of my hemoglobin, there is this thing called a heme, and it has an iron in the middle of it, which is what my oxygen will attach to, or my carbon dioxide will attach to. Does anybody, actually, nobody remembers, I won't say nobody, but very few of you actually got the bonus question right. But does anybody remember how many hemoglobin molecules there are per single red blood cell? We're gonna ignore the first group, they don't exist right now. I don't see you, you're dead to me. No? 280 million, there are 260 million drops of red drop, good God. 260 million red blood cells and a drop of blood, but 280 million hemoglobins per red blood cell. So 280 million times 60 million in that sense. So 260 million red blood cells, but each red blood cell has 280 million molecules of hemoglobin. Now, with this idea, we got to talk about this. My general rule of chemicals and proteins. What is that general rule? When chemicals land on a protein, what happens to the protein? Changes shape. So now you are a grandly made hemoglobin molecule. You have 4 irons in you, and they're all covered up. And somehow, we get the first oxygen to attach to that one first iron. Oxygen is a chemical. So what have I just done to my structure? I've changed it. I've made the second iron a little more exposable. In other words, we raised the affinity for O2 to bind. It is now easier to bind the second than it was the first. It's a chemical landing in a protein. What happens to the protein? Changes shape again. The third iron's more exposed than the second iron. So I've increased the affinity even more. Now it's even easier for the third than it was for the second. The second was easier than the first. Put that one on. What happens to my fourth affinity? Let's try that again. I had 1 oxygen. Is it easier to add the second? All right, what does that mean for the affinity? It means it increases. The desire for binding has increased. I add the third. What happens to my affinity? Does it increase? Yes. Okay. I add the fourth. What happens to my affinity? Well, I'm bound, right? But I've got all 4 on there, right? This has a really high affinity, all right? Or that has a really high affinity for that last, like it's greedy as all hell. Gimme, gimme, gimme. So I attach to it. I'm now going to go to my tissues that require oxygen. Take my oxygen. Take my blue oxygen. Too bad. So sorry. Right? That's a problem. Right? Having high affinity doesn't make it easy for cells to take that oxygen. When you think about affinity and binding, if it's easy to bind, it's not going to be easy to let go. If you're easy to let go, it's not easy to bind. You can't have it 2 ways. So I have to somehow alter hemoglobin's desire for hanging on to the oxygen, which we're going to do a bit today. So affinity, that's high. High affinity means a strong desire for binding. Low affinity means a low desire for binding. And then you want to think of the consequence of high affinity. If I have a high desire for binding, that means I have a low desire for letting go. If I have a low desire for binding, that means I'm really wanting to let go of it. And we have to change that problem. So what's going to cause hemoglobin's affinity to vary, to change? Are we looking at different conditions that would cause hemoglobin's affinity to vary depending upon the environment it finds itself in? We're going to look at O2, pH, and temperature, and then just mention the idea of what's known as 1,3-diphosphoglycerides inside of red blood cells. So your favorite topic, besides areas under a curve, is actually reading a graph. You gotta make you really skilled at reading graphs and make your life a lot easier. So, x-axis, is that dependent or independent? That was slow, right? X-axis is independent, y-axis is dependent. What is on the y-axis? Percent of saturation. In other words, how saturated are the oxygens? A way to think about that is, for any given hemoglobin, how many of its 4 irons are actually occupied by oxygen. If I have 4 irons and I have 4 oxygens, I'm totally saturated. All right, I'm 3 sheets to the wind, which we'll discuss that later. If I only have 2 of them on, I'm 50% saturated, right? I'm half loaded with this. So now when you look at this table we have in the lower hand corner, here's my partial pressure of O2s in millimeters of mercury, and what this graph says is that if my hemoglobin finds itself in an environment of 100 millimeters of mercury of PO2, then I'm roughly, basically, for all intents and purposes, completely saturated. This is an average of all of your hemoglobins put together. So there could be a lot of them that are actually at 100% and a few that are a bit less. Now, keep in mind when you guys look at graphs, right? Slopes are about rates of change. It's actually a very important thing to keep in mind. So here it's a relatively kind of somewhat flattened region, not much of a rate of change. I can even see that numerically, that if my if my partial pressure of O2 goes from 100 to 80, right, that's a 20 millimeter mercury change. But I only had a 3% saturation change. That's like, duh, why even worry about that? Right? Where do I find my most noticeable rapid change? It's right here. If you did a tangent line, right across the line right there. And it corresponds to a PO2 of 40, in which case I'm at 75% saturation. I experienced a 60 unit value drop in partial pressures of O2, right? A 60 unit drop, but I only had a 25% change in saturation. But for every unit of PO2 less than 40, right, my rates of change get steeper, right? From 40 to 30, right? That's a big change. That's more than 3. It's more than 25, almost. So we got to look at this 40 and realize that it should remind all of you of something, because I know you spent nothing but the weekend studying that little diagram of all your partial pressures of O2 from the atmosphere to the lungs to the heart, from the heart to the tissues, from the tissues to the venous system, back to the heart again. It was all in one breath, by the way. Because right there, there's your PO2 of 40. So what that graph says is that as blood comes by, and my hemoglobin comes by my tissues, how much of its oxygen does it give as it passes by an environment of PO2 of 40? Well, we went from 100%, right, to 75%. So that's a 25% decrease, which Dave is trying to say, well, dude, you only have 4 oxygens and you lose 1, right? It's from 100% to 75%. In other words, you gave off 1 of your 4 oxygens. Then you go back to the lungs and you get filled back up again. But what if the tissues were less than 40? What if they were 30 or 20? Then my partial pressure of O2 is lower, and so is my saturation. Right? I have less binding of oxygen to my hemoglobin. I can even just see this. Don't even have to be able to understand the curve of the graph, but just simply look at the numbers. High PO2, high saturation. The lower my PO2s, the lower the saturation. But the most significant change doesn't happen until you get to about the PO2 of 40. And then after that, every unit of change getting smaller gives us more significant changes in saturation. So if I look at that, look for a pattern. Don't say it out loud. Don't say it out loud. But look to yourself for a pattern of what you notice in terms of the partial pressure of O2 and the saturation of hemoglobin. There's a very obvious pattern. The pattern should be high PO2, high saturation. Low PO2, low saturation. They go hand in hand. As your PO2 value is lower, so does my saturation. You need to get to it, that's easy. So what it's trying to say is that as I go to the lungs, I find myself in an environment of high O2. That makes me have a high affinity. I'm going to really want to bind to all those oxygens because I'm in a high PO2 environment. I then leave the lungs, go down to the heart, get pumped out of the heart. I go down to the tissue capillary levels, right? Now here's my tissues. And what is their partial pressure normally? It's 40. It's a lower PO2. That makes me not be quite so cranky, more wanting to share. Because if I kept my high affinity and he tries to take my oxygen, it ain't going to work. but because of the chemistry, that low PO2 makes me have a lower affinity, right? Now I gave him my one oxygen. Now what happens to the ability to give off my second compared to my first? It's the same rule I've been trying to teach you guys about chemistry and about chemicals and proteins. When chemicals come off, what happens to protein structures? They also change their shape. It's easier to give off the second than it is the first, which is nice because if my tissues get even lower, like a 30 or a 20, you must really need my O2. So I better want to be able to give you my extra O2s if you're really in demand. That makes some sense, right? So you just simply look at the relationship between partial pressures of caffeine and PO2s, right? And your percent saturation. The higher the PO2, the higher the saturation, which means the higher the affinity. The lower the partial pressure, the lower the saturation. Yeah, but it also means the lower my affinity. Low affinity means I want to give.
So does that mean, for example, somebody's doing some anaerobic thing like lifting weights or sprinting or something, they're gonna strip more oxygen molecules off of their red blood cells once they sort of start catching their breath, and because their cells are depleted.
Well, they'll be even stripping them off as the blood cells go by the capillaries, but you also get things like myoglobin, and you have dissolved O2 in the plasma, but all those things, yes, the more anaerobic I do, the more I'm depleting my red blood, because that's why you can do anaerobics. I mean, how many hemoglobins in a single red blood cell? How many hemoglobins in a single red blood cell? 280 million, right? And each one of those little buggers has 4 oxygens. So do 4 times 280 million. That's how many O2s are in one red blood cell. How many red blood cells in a single drop of blood? 260 million. How many drops in a milliliter? Let's call it 20. How many milliliters in a liter? By 1,000. And then times 5. Right? So you have a lot of O2, which is why you can hold your breath and do things. You don't need to breathe to get those short periods of bursts of activity, because you have all that hemoglobin with all its strong desire for binding. Now let's look at the next little graph about this, because it's the same thing. This is known as a hemoglobin saturation curve, by the way. Put that name over here. Hemoglobin saturation curve. Because then it's about the saturation of hemoglobin, and it's a curve. Or if you want to probably use the word graph. But it simply shows the relationship between the partial pressure of O2 and hemoglobin's affinity or saturation level. We'll come back to that. Let's look at this one. Get rid of all those lines for a second, because for the moment I don't want them there. Hey, I said, go away. All right. So another nice little fun graph. We're doing 2 things at once on this graph. Yes, we're looking at the partial pressure of oxygen in an environment, right, which is that. But I'm also looking at the effect of pH. So my curve shows me is 3 different plots, right? The blue, the purple, and the red. This could be one of 2 scenarios. Let's make it the easy one first. This is John at rest. My pH is normal, 7.4. What if you, no, let me ask you this. First row, be quiet. 7.4 to 7.2, am I more alkaline or more acidic, everybody? More acidic, good, all right, the lower the pH, the higher the acidity. So what if I go from the purple line to the blue line, I become more acidic. You then follow the plot of that curve for the corresponding PO2 values, right? The blue line, is it to the right side of the purple line or to the left side of the purple line? It's to the right. That's why it's called the right shift. The 7.2 is a right shift compared to the 7.4. Right shifts always indicate a lower affinity of hemoglobin for oxygen. Right shifts always demonstrate a lower affinity that hemoglobin has for O2. Meaning, under that condition, for any value of PO2, it's easier for hemoglobin to want to let go of its oxygens. And let's see why that would be true. Why would you become more acidic? Any ideas? What would make you become more acidic? Which?
If you're sick.
Now, okay, let's not make you sick. And that could, yes, acidosis. I'm going to ignore the first row. They're dead to me. They don't exist.
Is that like when you're working out?
Why? Why do you think you're working out? Like eating a banana?
No.
Make me hungry.
Because you're the pyruvic acid? No.
Oh,
That-
pyruvic acid?
So
What does
not
that
acid.
become if it doesn't get used? If the mitochondria have enough oxygen, your oxygen debt, what happens to pyruvates? They convert it into lactic acid, lactates, right? That is an acid. What do acids do to an environment? It makes them more acidic. So by becoming physically active, right, you could become metabolically acidic. Now think about this. Before you guys start writing, we'll go through the whole scenario again. If you're becoming more acidic, that was because you created lactate, right? All right. Why did you create lactate? Because you couldn't convert the pyruvates into the little subunits for the mitochondria to use because you were lower in oxygen. Why were you lower in oxygen? Because you're running your butt off. Right? The more active you were, the more O2 the mitochondria needed. If you don't give them enough O2, then you get a buildup of pyruvates, which get converted into lactates. So why not have an oxygen transport system that says, you know what, I can respond to your acidity. I will help you maybe not become acidic by making it even easier for me to give you my oxygen to maybe prevent the inability to turn pyruvates into lactates. Because they're related. Do you guys see the connectedness to that? Yeah, no?
Yeah.
You gotta think about why you guys had oxygen debt. Right? Low levels of O2, mitochondria can't keep up. But why are you low in O2? Because the hemoglobin haven't changed their personalities. You need to make them have a lower affinity. So evolution designed them to respond to acidic environments. The more acidic you are, the lower my affinity becomes. It's easier for me to give you my O2, because apparently you're huffing and puffing and working your ass off and you need that extra O2. Now look at the red line compared to the purple line. To what side of the purple line is the red line? So what are you going to call it? Just call it a left shift. What happened to the affinity, do you think, of hemoglobin with a left shift? That was a weaker response, right? It's going to go up or go down? It's going to go up, right? You have a higher affinity, because it's the opposite of the other idea, right? 7.4 is normal. 7.2 is more acidic, a lower affinity. 7.4 is normal. The 7.6 is more alkaline. So I don't need to be easy to get off my oxygens. So I can then increase my affinity with that. So now we've seen the idea of how hemoglobin will change its affinity based upon PO2 values, right? And then even with changing PO2s, I can add another layer of influence by your acidity, by your pH values. Now with this, going from the purple to the blue, so in my mind it was UW to Boise State, right? Is what's called the Bohr effect. That is the only shift that has a name. This is the only graph you have a name to a change in the line. The right shift is called the Bohr effect. The left shift didn't get a name. And nobody else has a name either. So if someone says they study the Bohr effect, you realize it is a influence of pH values on hemoglobin's affinity. Now let's try and do this. Control Z. Yes, the undo screw up button. Yeah, I did that a lot this weekend. All right, here's how we're trying to show you. So I know PO2 is 40 is normal, right? And that would correspond to my purple line at about 75%. And so now what we're trying to say is that if I became more acidic, then where does the blue line connect with the intercepts of my X and Y? Well, here's the 40%, or the partial pressure of 40, pardon me, not 40%. The partial pressure of 40, it now hits the blue line, At about maybe 60? Is that less saturation? All right, that's less than 75, right? I have fewer oxygen molecules at 60 than I did at 75. That shows you I had a lowering of my affinity because I was allowing to let go of more oxygen. I went from 75% to 60%. If I go to the red line, that's at 80%. I'm actually hanging on to more O2s at the same PO2 value with those. I think we can do this. Oh, it doesn't show up in that mode. All right, so there's the purple line intersect, there's the blue one, and the red one didn't come through. So let's look at this one. Oh God, more lines. You guys are the orange. On average, 38 degrees Celsius. So the orange is normal. Is the red hotter or cooler? It's warmer, right? Okay. Is the red line to the right of the orange line?
Yes.
What kind of a shift would that be then? What kind of change in affinity? Lowering. Perfect. So you guys are getting the hang of this. Anything to the right of normal is going to be a lowering of the affinity. Anything to the left of it is going to be an increase in affinity. You just memorize that. But now see how it makes sense. When, besides being sick, would you be warmer? Because you would with the flu, right?
Also, if you're working out.
I don't think these people would work out because they didn't even offer that explanation, right? When you guys go run 20 miles, right? Aren't you hot as hell when you're all done? Right? And you're puffing your ass off, and you're just pouring down sweat, right? Your pH has dropped, your temperature's gone up, right? And what does temperature have the influence on your hemoglobin's affinity? Well, apparently, it lowers the affinity. Because if you're warmer, you're more active. If you're more active, you need more O2. So your temperature of the tissues influences hemoglobin's affinity by lowering it. Now, if I make you cooler, then I'm increasing the affinity. And the cooler your temperature becomes, the higher hemoglobin's affinity is, and the more it hangs on to that oxygen. Which is maybe one reason why people survive being drowned under hypothermic conditions. It's because they're hanging on to a lot of that oxygen. What you got to do is understand the basic idea of a hemoglobin saturation curve, right? Corresponding levels of PO2 and its influence on hemoglobin saturation. Then you simply say, well, how does pH affect that as well? On top of the PO2 values. Right? The more acidic, the lower the affinity. Then how does temperature affect that? Whoops. Then the higher the temperature, the lower the affinity. So I have higher temperatures, I'm more acidic, and low on PO2, I have really, really low affinity. Because apparently I'm hot, I'm acidic, and I need lots of oxygen delivered to my cells. And they all work together to allow hemoglobin to want to give up that oxygen. Remind you guys of the structure of fetal hemoglobin. Remember they have alpha and gammas. They have 2 alphas and 2 gammas. We got to remember that. Remember the gamma part has a higher affinity compared to the beta. And this is why fetuses can extract oxygen from the placenta. The gamma has a higher affinity, bless you, than the betas do. And we need to look at yet another saturation curve. Oh my God. All right, so let's put this in visual context. Fetal hemoglobin. Whoops, lost an oxygen. Where do I get my oxygen? In the lungs? If I'm unborn? That's why you guys have the foramen ovale and the ductus arteriosus, right? To bypass all that garbage. I get it from the placenta. Well, so the whiteboard's mom's blood. This is my blood supply. How do I get the oxygen from mom if we have the same hemoglobin structure? If we have the same affinity, if we have the same hemoglobin structure, I need some way to literally steal the oxygen from mom. That's why evolution created the gamma. I don't know if they created, but that's why we have the gamma protein. It has a higher affinity than mom's alpha beta. That allows me to literally steal the oxygen from mom's blood supply. Because I have a really high affinity. All right, higher than normal. You have the same problem. higher than normal, right? I go to fetal tissues. Fetal tissues want that oxygen, right? They're not going to get it unless I really change my affinity. So we know 3 things that would cause hemoglobin to change its affinity. What are those 3 things? pH, temperature, and O2 values, right, of tissues, all right? Well, if you look at the graph, we'll get the P50 value in a second. The green line corresponds to fetuses' tissue values of PO2. They are significantly lower than texting on phones. They're significantly lower than mom's tissues. The lower the PO2, what happens to affinity? The lower the PO2, what happens to affinity? It goes down. The lower the PO2, you're asked backwards, dude. Right? The lower the affinity, the lower the tissues. And that's right, the lower the tissues, the lower the affinity. So, given that gamma, with a really high affinity, allows me to steal the oxygen from mom's blood. That's great. High affinity. Then I go to the tissues. I have a high affinity. But you have a really low PO2. That really low PO2 allows me to really lower my higher than normal affinity. Otherwise, you're screwed. You're not going to get oxygen from me. You compare what mom's normal PO2 value is, right? That's around a 40. For normal tissues, right, we're doing a different thing here. I didn't put it in there. So mom's normal would be right about here. So we'd extend that all the way up to the red line, all right, and we extend the green to right there and just disappear that for a second. All right, and I can look at 2 values for mom. Why are fetal tissues so much lower in O2 compared to adult tissues? What are you guys really not doing any more of? You're not really growing anymore. You're done growing. You're cell replacing, yes, but you're done growing. What are fetuses doing? They're growing like hell. Metabolic activity is really, really, really ramped up. They need lots of O2. Because they need lots of O2, they have much lower PO2 value. And that much lower natural PO2 allows me to lower my affinity even with my higher than normal affinity for hemoglobin. So I can get the oxygen from mom, I'll be able to deliver it to the tissues. When you're born, you start to lose that gamma protein because you don't need it anymore because now you're doing external respiration with your lungs. And so over a period of years, you will no longer make that gamma protein. You'll convert to making alpha betas with your hemoglobin structures. Let me give you guys say about a 10-minute break. All right, and we'll start talking about transportations of these dissolved gases as we go through all this. Think about your saturation curves, make sure you understand them, so if you don't quite get them, we can try and address them when you guys come back from your little 10-minute break.